Okay, so this is section 1.1 to 1.4. We are looking at normal stress from an axial load, from axial. So normal stress is a sigma, and axial is going to be that internal N divided by A. So if we're given all these forces, length DC has a 5-inch square cross section. Length CB has a where is CB? Actually, it says a 12-inch diameter BA. So here's something that you all need to take note on. On exams, sometimes we're going to tell you, this actually came off an exam, 5-inch square. If I'm looking at, I know that normal stress is that internal normal over area. Is this an area? Is it 5 inches squared? Like it's a square area with 5, or is it a 5-inch square? It is units of a single inch. That means that my cross section is a 5-inch by 5-inch square. So the area is actually 25 inches squared. Okay, you have to look at units. 15-inch square. It's a 15 by 15. Okay, so my area is 15 times 15 inches squared. This individual inch tells me that's not a units of being squared. It's singular inch. So always look at your units. Okay, we are definitely looking at axial loads going through the centroids, normal stress, and we call this a cake problem. Cake problem, because it looks like a wedding cake. Okay, so if I'm going to find internal normal forces, I have to segment and find 3 free body diagrams. So I'm going to have a free body diagram, and I have an external of 1500 kips. Internal, I'm going to assume positive from D to C. Okay, I'm assuming that's positive. Summing forces in the y direction up is positive. So behaviorally, I'm assuming tension. Directionally for statics, for equilibrium. Okay, so I have minus 1500 kips minus my normal CD equals 0. So my normal CD equals negative 1500 kips. So I know that my normal CD is 1500 kips in compression. Okay. Then I'm going to take my Post-it note and I'm going to move it down ever so slightly. Okay, I'm not considering cross-sectional areas yet. I'm just trying to find internal normal force from C to B. And I have 1500 kips here. And this time I have 5000 kips that I can see. I'm not including anything else, but I have to include everything above or below. Summing forces in the y direction, up is positive, minus 1500 plus 5000 minus n equals 0. So my internal normal force, okay, that internal normal force, I get a positive 4500 kips. So I know that my normal is 4500 kips and we are in tension. Okay, the only time that we say it's tension compression is with normal forces. A lot of you all on your reactions at a pin, like if you have a pin right here and we have AY and I get positive AY, you're like, AY is in tension. No, it's a pin. It's not in tension. Implies literally tension is it's the normal force. It's either in tension or it's in, we're smushing it, it's in compression. Okay, so tension. Okay, then I do the same thing here. And you can quickly see I'm compression, tension, compression. So I'm going to end up with an internal compression. And you all draw it out on your own. Draw your free body diagram, draw and calculate, and you should find that our internal normal force from B to A is negative 13,500 kips. Okay, so we are in compression. So I could go on the side now over here, and if I wanted to draw a normal force diagram, here's my normal force, we are in kips. I'm going to call this side negative, which is compression, and this side is going to be positive, which is tension, and I have 1500, so I have a negative 1500. I have a positive 4500, and then I have a negative 13,500. So I've drawn tension or compression, tension, compression. There's my normal force diagram. Okay, how do I find stress? The stress in A to B has to equal the normal force from A to B divided by the area from A to B. Okay, so what is my internal normal force? I can look at my diagram. I could look at what I've calculated, negative 13,500 kips, because it is in compression. I have to put that negative in there, divided by 15 inch times 15 inch. Okay, and when I divide this out, then I'm going to get the stress of negative 13,500 divided by 15 times 15, and I get that internal stress is a negative 60 KSI. Remember, stress is kips per inch squared. That tells me it's 60 KSI in compression. Okay, in compression. And I can do the same with all of those. And then I can draw a stress diagram. I could actually then do the stress in KSI. Here's tension, here's compression, and I'm going to find that I had 60 KSI in compression. I'm going to have 40 in tension, and then here I've actually back at negative 60 in compression. Well, wait a minute. How can this top one be 60 in compression and the bottom one be 60 in compression when the top one only had 1,500 kips and the bottom one has 13,500 kips? Well, they have different cross-sectional areas. Okay, they have different cross-sectional areas. So they could have the exact same stress even though they have different normal forces because they have a different cross-sectional area. Okay, a different cross-sectional area. And so this would be a stress diagram. Okay, what if I wanted to show the stress on this bottom block? So here's my rectangle, and I know that we are in compression, so we have to be going down. And so I have an average stress, so it looks like, you know, some sort of a rectangle pushing down. And my stress is, I'm showing it down, so I'm going to call it positive 60 KSI, a magnitude of 60 KSI, because I'm showing you directionally it is in compression. I could take a little tiny block out, like so. And on this block, I could show you 60 KSI stress. I could show you on this little tiny block. I could also show you 13,500 kips. So I'm showing you it's in compression. I don't need to put a negative because you can physically see it. I'm showing you it's in compression, so I don't need to tell you it's negative 60 KSI. I'm showing you it's in compression, or I can tell you it's negative 60 KSI. So whether I do a chart or I show it on the cross section, or I give you a stress block, they're all showing me 60 KSI in compression. Easy peasy.